In this video, I'll introduce the current divider formula. The current divider formula allows us to easily determine the current in one of the resistors in a parallel combination of resistors, if we know the total current into the parallel combination. Keep in mind we're still applying KVL, KCL, and Ohm's law. We're just applying them in one easy-to-use package. Before we determine our current divider formula, let's quickly review parallel resistances. A parallel combination of two resistors has an equivalent resistance that's equal to the product of the two resistances divided by the sum of the individual resistances. Now let's see what we can find out about the individual currents through the resistors in this circuit. This current, I1, is equal to this voltage, V, over R1. Likewise, I2 is equal to V over R2. The voltage-current relationship across these terminals is V over I is equal to R1, R2, the product of the two resistances, over the sum of the two resistances. So V is equal to I times R1, R2 over R1 plus R2. Just multiplying through by I. If I plug this V in here, I1 is equal to 1 over R1 times V, which is the total current I, times the product R1, R2 over R1 plus R2. This R1 cancels with that one, so I1 is equal to the total current I times the other resistance, R2, over the sum of the two resistances. There's one of our current divider relationships. If I do the same thing, I2 is equal to the total current I times the other resistance, R1, over R1 plus R2. There's our other current divider relationship. The current divider formula says that the total current into a pair of parallel resistors is divided among the individual resistors. So if we have a pair of parallel resistors in which we know the total current I into them, we can really easily determine the current through the individual resistors. The current through resistor R1, I1, is equal to the total current I times the other resistance, R2, over the sum of the two resistances. Likewise, the current through resistor R2 is the total current times R1 over R1 plus R2. So for the case of two and only two parallel resistors, the current through one of the resistors can be determined by multiplying the total current times the resistance of the other resistor and dividing the result by the sum of the resistances. Finally, before we do some examples of how to use our current divider formula, let's derive a general current divider formula. We have n resistors in parallel, R1, R2, up to Rn. I want to find the current I sub k through the kth resistor in that combination if I know the total current into the resistors I sub s. Since these are in parallel, they all share the same voltage difference, V sub s. Now, I sub k is equal to V sub s over R sub k. We also generated the voltage-current relationship for a set of arbitrary number of parallel resistors. That was Vs over Is is equal to 1 over R1 plus the inverses of all the other resistors up to 1 over Rn. Now going back to this formula, I sub k is equal to V sub s. If I multiply this through by I sub s, that's I sub s over 1 over R1 plus 1 over R2 plus up to 1 over R sub n. This is V sub s. I divide that by R sub k, and rearranging that slightly, I get I sub k is equal to I sub s. Bringing this resistance in here is 1 over R sub k over 1 over R1 plus 1 over R2 plus 1 over Rn. That's our general current divider formula. We can't convert this to a product of resistances over a sum of resistances because the math doesn't work out. I have a 2 amp source here that's providing power to these 3 resistors, all of which are in parallel. I want to find the current through the 6 ohm resistor. I have a set of parallel resistors. I know the total current going into those resistors, and I want the current in one of the resistors. This is a perfect application for our general current divider formula. So I is equal to the total current, 2 amps, times the inverse of this resistance, 1 over 6 ohms, divided by the sum of the inverses of the individual resistances. 1 over 2 ohms plus 1 over 3 ohms plus 1 over 6 ohms. 1 over 2 plus 1 over 3 plus 1 over 6 is just 1. So this is 2 amps times 1 over 6, which is 1/3 of an amp. We could also reduce this circuit and then use our special formula for 2 resistors in parallel. So we can combine these 2 parallel resistances into a single equivalent resistance. Req is equal to the product of the 2 resistors, 2 ohms times 3 ohms over the sum of the 2 ohms plus 3 ohms, which is 6 over 5 ohms. The circuit now becomes a 2 amp source with this equivalent resistance, 6 over 5 ohms, in parallel with our 6 ohm resistor. And we still want to find this current I. Now we know the total current going into a parallel combination of 2 resistors, so I is equal to the total current, 2 amps, times the other resistance, 6 over 5 ohms, divided by the sum of the 2 resistances, 6 over 5 ohms plus 6 ohms. 6 over 5 plus 6 is 6 plus 36 over 5, so this is 2 amps times 6 over 5 divided by 36 over 5. The 5's cancel. 6 over 36 is 1/6, so this is 2 amps times 1/6, which is 1/3 of an amp, and we get the same answer. In this example, I want to find the resistance R that gives me a 2 milliamp current here. I have a 6 milliamp source, so I know the Yep. In this example, I want to find the resistance R that will make I 2 milliamps. I have a source giving me 6 milliamps, so I know the total current into the parallel combination. I want to find a current in the parallel combination so I can use my current divider formula. So I is equal to 6 milliamps times the other resistance, 2 kiloohms, over the sum of the 2 resistances, 2 kiloohms plus R. We want I to be 2 milliamps. So 2 milliamps is equal to 6 milliamps times 2 kiloohms over 2 kiloohms plus R. If I divide through by 6, I get 1/3 is equal to 2 kiloohms over 2 kiloohms plus R. 1/3 is equal to 2/6. So I have 2 over 6. R has to be 4 kiloohms. Using the current divider formula can make a circuit analysis considerably simpler, since you're combining KVL, KCL, and Ohm's law into a single equation. However, before you apply the current divider formula, make sure that the resistors you're applying it to actually are in parallel. If you're in any doubt about that whatsoever, doing KVL around a loop containing the candidate resistors will solve the problem. In the next video, I'll use voltage dividers, current dividers, and circuit reduction to solve some circuit analysis problems.